You know, we see the sun pretty much every day. It's the most familiar thing in our sky. But what if I told you that the most important parts of the sun, the regions that control its entire 11-year cycle of activity, have been completely invisible to us? Well, until now.
And we're not talking about some mystery buried deep down in its core. Nope. These secrets are hiding in plain sight, in these vast, unexplored territories that we are only just now beginning to see for the very first time.
We are talking about the sun's poles, the very top and bottom of our star. You can think of them as the last great uncharted frontier, right here in our own solar system.
The problem is really just simple geometry. You see, Earth and all of our telescopes, we orbit the sun on a flat plane, kind of like a cosmic racetrack. This means we only ever get a side-on view. We can see its equator, its waistline, perfectly, but its poles have always been distorted or just completely hidden from sight.
So why are we so obsessed with these hidden regions? I mean, who cares, right? Well, it turns out the poles aren't just quiet, empty spaces. They are the command center for the entire sun. The incredibly powerful magnetic fields there act as the sun's memory for that 11-year cycle. And get this, their strength can actually predict how stormy the next solar cycle is going to be.
So to solve this mystery, you can't just build a bigger telescope on Earth. That's not going to work. You have to literally change your perspective. You have to send a spacecraft on an incredibly daring mission to fly over the top of the sun. And that is exactly what we did.
So meet the hero of our story, the Solar Orbiter. This amazing ESA and NASA spacecraft was designed for basically one primary reason: to leave that flat orbital plane and give us our very first clear, direct, top-down look at the sun's poles.
In March of 2025, it began its big campaign. For 8 days straight, its advanced instruments were pointed directly at the sun's south pole, just capturing data that scientists have, and I mean this literally, been dreaming about for decades.
So, the billion-dollar question: what did it see? What does the top of our star actually look like? Okay, to understand what we're about to see, there's one key concept: supergranulation. It sounds complex, but just picture a huge pot of boiling water. Hot water rises in the middle, spreads out, cools, and then sinks down at the edges. Well, the sun's entire surface is covered in these massive boiling cells of plasma. And here it is. And I want to be super clear. This is not a simulation. This is a real image from the Solar Orbiter looking straight down at the South Pole. It's this incredible, corrugated, rippling landscape of churning plasma. Each one of those cells you see is a supergranule.
And the scale here is just staggering. A single one of these convective cells can be 20 to 40 megameters across. To put that into perspective, that's up to 3 times the diameter of the entire planet Earth, just one of those bubbles.
Now here's where it gets really fascinating. On the left, you're seeing that plasma flow. On the right, you're seeing the magnetic field. That churning motion of the supergranules, it acts like a bulldozer, sweeping up and concentrating the magnetic field at the edges of the cells. This is what creates that vast, almost lace-like magnetic network across the entire pole. But hidden within all of this chaotic boiling, scientists found something else: a faint but persistent, large-scale motion that had been theorized about for years, but had never, ever been directly observed.
So how'd they find it? They couldn't just watch the plasma bubbling. They needed to track the magnetic field for a really long time. So they focused on these little bright points you can see here. Think of them as tiny, bright buoys floating on the solar ocean, perfectly tracing the underlying magnetic field over many, many days.
So by tracking thousands of these bright points over that full 8-day observation period, they built this map. And this is the aha moment. It shows the latitude of the features over time. And just look at that. The tracks aren't random at all. There is a clear, undeniable slant, a steady, consistent drift of the entire magnetic network, all moving towards the pole. They clocked its speed at an average of between 10 and 20 meters per second. Now that sounds incredibly slow, doesn't it? You could outrun that. But for a star, a persistent one-way flow at this speed, happening across millions of square kilometers, that is a titanic force with absolutely enormous consequences. What they found is, for all intents and purposes, a magnetic conveyor belt. It picks up the magnetic leftovers from sunspots down at lower latitudes, and then slowly but steadily carries them all the way to the pole. This is the very mechanism that builds up the sun's powerful polar magnetic fields.
And this discovery, it isn't just a neat little detail. This forces us to actually rewrite our understanding of the sun's engine, the solar cycle itself.
For years, our best models, which were based on those blurry side-on views, they all predicted that this conveyor belt would slow down or even stop at around 75 degrees latitude. But Solar Orbiter's direct view shows us that is flat out wrong. The flow continues, totally unabated, all the way to the pole itself.
So why does this matter to you and me here on Earth? Because this flow is the key to building those polar fields, which in turn predict how intense the next solar cycle is going to be. By feeding this new, much more accurate data into our models, we can get way better at forecasting space weather, and that means we can better protect our satellites, our power grids, and even astronauts from the sun's most violent outbursts.
What this all means is that we have finally, for the first time, witnessed the physical mechanism that drives the sun's 11-year heartbeat. We have gone from just theory and models to direct observation of the solar engine in action.
And this all leaves us with one final, pretty profound question. If we were this wrong about something so fundamental, what other secrets is the sun still hiding from us?